So I was saying about we'll have this problem with 10 squares missing, so you need to do the calculations. We'll have multiple choice questions on characteristics of the system. I'm saying it again for the video. And then we'll have partition function calculation. And then I want you to walk me through the dependence on temperature. So like if you've got Q and you've got the equation, and I say if temperature goes to infinity, walk me through that equation to get to Q. As temperature goes up, this piece goes down. As this piece goes down, this goes up. That, vice versa. As you just follow through sort of the order of operations and getting from temperature all the way out of that equation and to Q. So if temperature goes to infinity, what happens to Q? And then as temperature goes to 0, this piece goes to 1 or goes to infinity. And dividing by infinity is 0 and those kinds of things to where we didn't see what Q does. Okay, so that's a written one. So there'll be one written equation, the question about temperature dependence on a particular equation. And then I may do one of those proportionality ones where you don't know all the information, but you know how it's proportional to some variable. And so you need to do the ones and twos, the fraction, and we can do a couple of those. We can do examples of all of those ones. So we've gone through USHAG through a couple of lectures. You've got the sandbox, so you guys can work on that yourselves. But this morning I want to focus on the partition function and on the temperature dependence type thing. And if you need review of what I call the ones and twos, the proportionality exercise. Okay. So. Yeah, so I think I won't waste time on the overlay. I'll try to figure that out on my own time. But was there any did you need any, or did you have any questions on the sandbox? Let's just say that. Shrink it down so we can see the whole thing. Are there any scenarios you want to try? Are you comfortable with the spreadsheet in terms of playing around with it? Have you played with it yet already? Anybody? You haven't played with it? No? Okay. A little bit? Yeah. Okay. So here's an example. Because of the degeneracy, let me just at least talk about this one that's shown. It's endothermic, but it's also spontaneous. And so that's kind of interesting, right? Normally spontaneous reactions. Let's just look at delta G here. This equation here, G equals H minus TS, it also works with deltas. So delta G is equal to delta H minus T times delta S. Okay. We have only one T. We don't have a delta T, but we've got T times delta S. And so that means that if we want a negative Gibbs energy, okay, if we have a negative enthalpy and a positive entropy, then it's going to be spontaneous no matter what. How do we get spontaneous, or how do we get an increase in entropy? Look at our products. We have lots of degeneracy. Okay, what's another way to get a huge entropy? Let's make this a two-level system. We're going to go over here. We're going to make this one. I'm going to make this one a 0. When I do 0 degeneracy, that energy level's gone. Okay, so that's one way to just sort of wipe that out. Okay, and so we've got 1 here and 0.14 there, and so we've got 87% chance of being in the ground state, and so then let's make this one 1 and 1. Okay. It's still, look, no degeneracy, right? Here's the products, no degeneracy. And yet it's still endothermic and it's still spontaneous. So what's driving it forward? It's not enthalpy, right? We want negative delta G's, and if you have a positive enthalpy, it's a problem, right? You're sort of you're not going to be spontaneous if the temperature is low enough. In fact, let's do that. Look at the Gibbs here. The Gibbs energy is -7, or let's say -59. Okay, let's start lowering the temperature. 100 Kelvin. -3.8. Why? Well, because the only negative piece is the minus T delta S, and delta S is positive. So the only thing making this spontaneous is the high temperature. If we lower the temperature to, let's see, we can get it to be like 80. Let's see, 1.5. Okay, 70. -0.8, just barely spontaneous. Okay, let's go to 50.1. Okay, yeah. It's probably going to bottom out at 1. Like if we go to 1 Kelvin, yeah, 0. But we have 2 ground states, and those are the only 2 things populated, right? But what we can do to make things spontaneous forward, even though they're endothermic, is to have closer spaced energy levels in the products. So you see right here, these energy levels are 0, 200, and 400, and this is just 0 and 400. So energy levels that are closer spaced, that also drives up entropy. And so it can be endothermic, but still have enough positive entropy to make it spontaneous. So everybody understand that? That's sort of the conceptual version of USHAG. So I don't want you to just be like robots and learn how to manipulate the equations. I'd like for you to see that spontaneity is a competition between enthalpy and entropy. If the reaction is exothermic, there's no competition, right? Because you're well, I mean, I guess your entropy could be negative, and that would make the T delta S piece positive. But if both the entropy is positive and the enthalpy is negative, which is what we have in almost all combustion reactions, I would say all spontaneous combustion reactions are exothermic, reacting with oxygen, giving off heat, and they're producing a lot of moles of gas. Remember, the gaseous partition function is translational motion, whereas a liquid is really not translating that much. It's not filling a whole room. Okay, so its motions are restricted to vibrations and maybe some sort of pseudo rotations. So liquid has a very restrictive energy landscape, but gas can go through the whole room and has 10 to the 30 energy levels populated at room temperature. So that really drives up the entropy. So entropy is positive, and it's exothermic. It gives off heat. So that's why it's so hard to put out combustion reactions, because they're so spontaneous. We have to stop the oxygen and the fuel from getting near each other. So but you can sort of see that here in playing around with these different problems. We could even make it like 100 here. Then it's very endothermic, and here we go, it's not spontaneous because it's uphill, right? We got the ground state here at 0, then we have 100, 200, 400, and but now if we increase the temperature, then we can make this go spontaneous. Let's go to 500. Yeah, -74 wave numbers. Okay, let's go to 200. Oh, I changed Boltzmann's constant. Let's go back up there. 200. Yeah. So it's endothermic and not spontaneous at 200 Kelvin. At 500 Kelvin, it's endothermic and spontaneous. So it's a good example. So these are some of the things that you can do with the sandbox. Just know how to calculate each individual square. Okay, let me bring up a PowerPoint that we can do some and use some scratch paper. Oh, you did? How?
You take delta H or if you take H equals U plus RT,
Mm-hmm.
Delta H would be H of the products minus H of the reactants. And if you substitute the formula for those, you have U of the products plus RT minus U of the reactants minus RT.
Okay.
RT stands on just U products minus U reactants.
Yeah, okay.
So I think they should always be equal H and U, or delta H and delta U.
Yeah, and then delta A and delta G, same kind of thing. Yeah. Like I said, I figured it was probably algebraically identical, and good job for that. Yeah. Okay, so now we've got, let me pull up the partition functions so we can do that temperature dependence. So let's pick one. Let's see, heat capacity. So I'm going to go all the way to the end of this one. Is there a summary? There's got to be a summary. Come on. There it is. Okay. All right, so let's put that up there. It won't let me kill that one. Okay, here we go. Now you can see it. Yeah. Okay, so what I was saying was if you have something like the translational partition function, this is this piece right here. Okay, so we would say that as temperature goes up, or we could do it this way. As temperature goes to infinity, you see temperatures in the numerator, then Q goes to infinity for translation, Q trans. Does everybody see that? Okay. And then as temperature goes to 0, Q trans goes to what? Also 0. And that's these. Remember, these are approximations, and so we know that that's not correct. Q would go to 1, but we would switch over to a countable system, and then we would just do the Boltzmann factors, just like USHAG. We would calculate Q, and it would be e to the minus 1, and it would be 1. But this equation is showing that Q trans goes to 0 as temperature goes to 0. Okay. This piece right here is the rotational piece. So here we have temperature again in the numerator. So as temperature goes to infinity, Q rho goes to infinity. Did everybody see that? And then as temperature goes to 0, Q rho goes to 0. So this, I'll put these pieces right here. I'll put a star by them. And over here I'll put and I say approximations fail as t goes to 0 because we know Q goes to 1 at t equals 0. Okay, and remember Q is, well, you tell me what Q is. If you were to describe Q to somebody, the partition function to somebody who doesn't know a lot of scientific terms, how would you describe it? Yeah, it's not the spacing. The probability of what? In fact, if they look at you blankly when you say probability, let's take that word off the table. The chance of what? In that state. Or instead of picking a particular state, how many states? Q is, oh, I don't want to give it to you. All right, I'll wait. There's a place in the notes where I say Q can be thought of as blank. The count of available energy levels. Yeah, so as temperature goes to infinity, there's an infinite number of available energy levels that are populated. So it is kind of a probability, but without using any scientific terms, it's just a count of the available energy levels. So this means as temperature goes to zero, there's only one available energy level, the ground state. Yeah, so it can't go to zero because we never have zero energy levels. The molecules have to be in a state. Yeah, they're described by a wave function, and that wave function has an energy, and we may set that energy to zero if it's the lowest one with no nodes. Remember all of that from the fall. Now, philosophically, what's keeping that state alive? We don't know. That's a philosophical question or a theological question. But we know the ground state is there, and you can't get below it. Okay. Let's do the last one. The last one's much more interesting. Okay. So for this one, for Vervive, right? Let's look at the pieces. So as T goes to infinity, let's do this in two columns, okay? Then theta over T goes to what? If you're dividing by infinity, you get 0, goes to 0. And then e to the minus 0, because that's in this exponential right here, does what? Goes to 1. And then the denominator is 1 minus 1. So this ratio, 1 over 1 minus 1, goes to infinity, doesn't it? So as T goes to infinity, Q goes to infinity. But it's a long path, right, mathematically. And so this is kind of what I'm looking for, you guys looking at the equations and giving me this little path. Let's do T goes to 0. As T goes to 0, then theta over T goes to infinity. Now, e to the minus infinity, what is that? Infinity, 1 and 0. That's right. All of the above, none of the above. Yeah. So think about just 10 to the x, right? 10 to the minus 1 is 0.1. 10 to the minus 2 is 0.01. 10 to the minus 3 is 0.001. So 10 to the minus infinity, 0, right? It's really, so it goes to 0 because essentially it's a infinite number of zeros with a 1 in the end. So the E is it behaves a similar way. So this goes to 0. And so then that's over here in 1 minus 0, right? This 0 becomes this piece right here. So 1 over 1 minus 0 goes to 1. Beautifully. So the vibrational one is not an approximation. That's why there's no star by that. It's exact. So I know that was a video lecture because of the snow day, but the snow day in quotes. But you know, we walked through this in that lecture, and we also saw that it was not an approximation; it was an exact solution. So it behaves well both at infinity, temperature infinity, and temperature 0. It goes to infinity when temperature is infinity, and it goes to 1 when temperature goes to 0. So that's beautiful. Okay, so let's go to the end of the slideshow.
I do have a question.
Oh, yeah.
So related to that problem, you have written down t squared over n squared b.
Yeah.
What is that in relation to?
T squared over. Okay, so that was for a diatomic. Yeah, for a diatomic, we only have two rotational constants.
Okay.
Yeah, and A is, I think it's A that's not defined, and B equals C. So rotation around the axis of a linear molecule is not defined, and then the rotation around X and the rotation around Y are the same because it's the same masses. So we lose the T cubed, we just get T squared, and we lose the theta A. So we have theta B, and that's equal to theta C. So it's theta B squared. Yeah. And then it's squared to the 1/2, and so it ends up being T over theta B. Yeah.
So that's for diatomic.
That's for diatomics. Yeah. Okay, that's good. Or linear, I should say linear. Yeah, linear, more specifically.
For the translational partition function,
Mm-hmm.
the part with the gas, is that only used when we're dealing with the gas? And we're not?
Good question. We have only been doing gases. So all of this has just been for gases, because it gets really complicated when you go to liquids. So we lose the rotational degree of freedom, and we lose the vibration, the translational degree of freedom. So you think of a mole of gas molecules, have translation is the biggest, and rotation is big as well. Vibration is almost nothing. Then we put them in contact with each other, and we don't lose. We shouldn't lose degrees of freedom, right? We still have X, Y, and Z freedom to move that molecule, but we just can't move it from one wall of the room to the other. So it has a smaller box. So it's still trying to translate, but now the whole molecule is banging against its little solvent cage or its little matrix. And so all those translational motions have now become vibrational motions. But the mass is larger. It's the whole mass of the molecule. And the box isn't really tight like a vibrational bond. It's a box that contains the whole molecule. But you can imagine that then you're dealing with, and also the box walls are not rigid. So it's not like our particle in a box where it has infinitely steep walls, because the box is squishy because it's the other molecules vibrating around too. And so this gets into sound waves moving through a material, and these are called acoustic modes because they're the same motions that transmit sound through a material and through the air. But we talk about solid materials. So those translational motions have now become acoustic motions in a material. And that is really where the different materials have their thermal properties. It's in these acoustic modes because it's how heat transfers from one corner to the other, one side to the other. And so that's where we really get into a lot of complicated physics, and that's what condensed phase physics is all about. So if this really like lights you up and that's what you love, you might looking at condensed phase physics or the application of that in materials science or in materials engineering. So this is really the exit ramp to engineering. So like if you're in an undergraduate program and you're getting your chemistry degree and you get to this course and you're like, wow, I love this. You know, you can keep your glassware and your stinky solvents. I want to get into the physical properties of materials. This is just dipping your toe into the shallow end of that pool. And so you could go into a master's program in materials science directly. If you wanted to go into like more of like a materials engineering, you're probably going to have to take some more courses like this in engineering at the undergraduate level. But that's okay. They'll probably accept you in the graduate program with a provisional acceptance, provided you do well in these 2 undergraduate courses. And so you take 2 undergraduate courses or so, and then you're kind of up to speed with the other graduate students, and then you can go into your master's program. So that's a different path that you may not have known was out there. Okay, so I said that we did the temperature thing. Now you should be able to calculate any one of these given the thermal temperatures, the rotational temperature or the rotational constants. Are you comfortable with going, like if you've got the let's say the vibrational temperature of, I just know, like for the CH bond is 3000 wave numbers. What is the rotational temperature? Theta CH. Now, I see rotational, I mean vibrational temperature. So like this one right here. You know how to calculate that? That's something you'll need to calculate. It's easier than you think. We just need to convert wave numbers to Kelvin. And do you know any of your constants that have both those units? Planks. We have a vote for Planks. Yeah, so we could do that. We could. This already is E over HC. Yeah, so that's right. If this was joules, then this is joules times seconds times centimeters per second. So the seconds are gone, the joules are gone, and we end up with inverse centimeters. But we've done another kind of thing. We did K over HC. And K over HC is that 0.695 wave numbers Kelvin wave per Kelvin. Okay, so we just take that number, 3000 wave numbers, and divide it by the 0.695. And so Kelvin comes up on top. So it's Kelvin to the -1 in the denominator. Both the wave numbers cancel. And so I don't know what this gives. This is like 4,000. Does anybody have a calculator? Or 316. Okay, Kelvin. So that's the vibrational temperature for the CH bond. So we would need, at least 4,000 Kelvin before that starts to get activated. Okay. Oh, there's another big part of the test, like 4 or 5 questions. Okay, and that's on calculating the heat capacities, for rotation, for vibration, for translation, and so on. So let's do those because we were talking. Let's see. Let me see if I can go to the end. Okay, so we can just do that here. So what's is CV? Someone give me a molecule. Water. Okay. Something more interesting. We've done water in the notes. Cyanide? Okay. Like hydrogen cyanide, like cyanide gas? Okay. HCN. Okay. Lewis dot structure, let's just verify that it's linear. Would you all agree that this is linear? Okay, good. So it's a linear molecule. So heat capacity for translational motion is equal to what?
3 halves.
3 halves NR. Okay. And the heat capacity for rotation is what? What's that? Yeah, 2 halves. Yeah, why 2 halves? That's why I was worried about it being linear. Okay, we're making sure, 2 halves NR. Because linear. Okay. So my shorthand makes sense. Okay. And then CV vibe. What's that? It's ANR. ANR. Okay. And what is A? A equals number of active. Oh gosh, what is that? Active vibrations.
Okay. Low temperatures, ground state is active, right?
Right. So didn't give you the temperature. So if I do that to you in a problem in the notes, you have to assume what? If I didn't give a temperature. I just said, what's the CV for HCN? Yeah, let's just go with 298 if I don't specify. Okay. So assuming T equals 298 Kelvin, A equals 0. Yeah.
So room temperatures.
Yeah, for vibrations. For vibrations, it's important. Room temperature is high for translations and high for rotations because those energy levels are really close together. But the vibrations, room temperature is low. It's all based on those either the thermal wavelength for translation, the rotational temperature for rotation, and the vibrational temperature for vibration. Vibrational temperatures are really high, so that means room temperature is low. But rotational temperatures are really low, which means room temperature is high. Room temperature hasn't changed, but the thermal, the spacing of the energy levels is different. So I drew this in the fall semester. The translational energy levels look like this, rotational energy levels look like this, and vibrational energy levels look like that. Okay, and so if you're at room temperature, you've got a lot of translation, a lot of rotation. So this is room temperature. A lot of translation, a lot of rotation, but almost no vibe. Only for really big floppy molecules will you start to see vibrational excitation. We did buckyball, and 33% of its vibrations were active at room temperature for gas phase buckyball. So we add all this up. The A is 0, and so it's really 5 halves. CV total equals 5 halves NR. So that's for HCN. We know what R is. If the problem gives you the number of moles, then you would need to just give a number. You can just calculate it that way. Okay. If you wanted to just leave it per mole, then you could calculate 5 halves times 8.314 joules per mole Kelvin, right? See the per mole is there waiting for you to multiply by the moles. 5 times 8 is 40, divided by 2 is 20, is about 20 joules per mole Kelvin. So you look at the answers and you're like, okay, there's one that's close enough to 20, I'll pick it. No calculator needed. Yeah, well, I left it per mole here. See, if you don't put N in there, if you don't multiply it by anything, then you have a per mole in the denominator. It's waiting to, then if you have 20 moles, then you multiply it, and then you end up with joules per Kelvin. Yeah.
So if you do a problem like this, are you going to do it like either way, so sometimes like this, or with the moles?
I don't remember, but just beware. Look at your units, right?
Mm-hmm.
If you have a number of moles in the problem and you just calculate it with 5 halves R, then you're ready to multiply by the 20 moles that's in the problem or something like that. Yeah.
If it wasn't linear, rotation would be 3 halves.
Yes. Yeah. And then it would end up being 6 halves or 3 times R. Yeah.
Okay, so 2 halves is 1, right? So
yes.
How does that math work? If technically it's 1, wouldn't it be halves and R?
We're adding. Yeah, we're adding. There you go. Yeah, very good. Yeah, that's right. No, that's good. Yeah, it's great.
And electronic never matters.
Yeah, it's because it's even further than the vibration. If you guys start like figuring stuff like that, where if I could just make this, if I could open up your brain and like wire that diagram in to your brain, right? Then you would just know things and not know how you know them. right? And just having an understanding of the energy spacing of translation, rotation, vibration, and electronic. That's like it's like that meme. I found the secret to life. The energy level diagram for those things. Just don't throw it away. You know how that guy does. I live in the memes. But maybe I'll send that to you. I'll make that up, and then you guys can know what I have in my head. It's pretty funny. So we did that. So there's, because again, I can ask you a translational one, a rotation, a vibration, blah, blah, blah. So that's like 3 or 4 questions right there, the CVs. What about what if I wanted to do the internal energy for this? And we're dealing with moles of molecules. So what's the internal energy of this? So just think about this. So let's say we have 1 mole. So we end up with 20 joules per Kelvin for the CV total. What's the internal energy of this molecule at room temperature? Well, we just multiply that dude by 298 Kelvin. So that's about 300. So that's 600, 6,000. So around 6,000 joules or 6 kilojoules. So at room temperature, this molecule has about 6 kilojoules of heat in it that it can do things with. And so if it's in a chamber with a flexible wall that can move like a piston, and the back pressure on that piston is less than 1 atmosphere, then it can push that piston using that 6,000 joules, and it can put a force on that piston and push it. And then when it expands, what happens to its temperature? It drops. It loses energy and it drops when it expands. So that's what the next part of the course is expansion and compression, and using the energy in molecules to do work. And the heat capacity is key to all of that. So we did USHAG so we could understand the bridge from quantum to thermal, and then we kind of hammered in the heat capacity stuff, because that's going to lead us right into the expansion and compression work that we can get out of these molecules. Still using gas phase. Even to today, all of our energy is dependent upon gas phase molecules pushing pistons or pushing turbine blades. So we spin turbines that spin generators that make electricity using steam. So even though we don't, you think we're not still in the steam age, we still are. Yeah, we still use steam power, because all of our power plants, with the exception of the natural gas turbine engine, all the other power plants just make steam, and the steam spins the turbine and the turbine spins the generator. So if we can get away from that, then our efficiency might skyrocket. The last part of the course, we talk about the efficiency of the steam turbine, and it's only about 46% efficient. So we're throwing away 54% of the energy, no matter what the source, whether it's nuclear or fossil fuels. We make heat with that burning coal or burning nuclear fuel, and then we throw away 54% of it by using a steam turbine. So if you want to be richer than Elon Musk, figure that out. Figure out how to go straight from that heat to electricity without going through a steam turbine. We do have thermoelectrics, like we have special Peltier cells that turn heat differentials directly into electricity. That's pretty cool. They're 4% efficient. So that's not going to work. It's a great idea, though. And maybe we can figure that out. If there's some new material or something that could break that secret. Okay, what else am I missing? USHAG. We did the temperature dependence thing. I had mentioned the Q1s and 2s or whatever. You saw that problem early on in the translation homework. Let me start another blank slide. Okay. Oh no, I went too fast with the wheel. That stinks. All right, we'll do this. All right, so let's go back here. We've got 4 minutes. Okay. So let's say you have some goofy equation, some process P is proportional to temperature to the 1/16th power. Okay, something strange, right? And we say, well, this process was equal to 5,000, and temperature was equal to 298 Kelvin. P equals question mark when temperature is equal to 10,000 Kelvin. Okay. Is that cool? And so you don't even know, like, how are you going to do this? Let's say, I mean, we could have all kinds of other constants in there, but all you really need to know is the temperature dependence, because you can do the ones and twos. What I mean by the ones and twos, you say P2 over P1 is equal to T2 over T1, everything to the 1/16th power. Okay, so there's your equation. We go from a proportionality to an equation, and then you can put in, you've got one equation, one unknown, because this is P2 over 5,000. We don't even know what the units are, but it doesn't matter. And then T2 is 10,000. Okay, and T1 is 298 to the 1/16th power. Okay, so let me get my calculator out. All right, so 33.55 is that fraction. Then I got to do the 1/16th. So, and I've got y to the x. Yes. So I get 1.2456 for the fraction on the right times 5,000. So P2 is equal to 6228. So we went up to 10,000 Kelvin, and it only went from 5,000 to 6,000. Does that make sense? Just looking at it. Yeah, because the temperature dependence is minuscule. It's to the 16th power. Okay. How far would we be off if we looked at this and we just did the regular old proportionality? P2 over P1 is equal to T2 over T1. So a lot of students mess that up. They forget the 1/16. Okay. So this is wrong. Okay.
So is that, did you just do the 1/16 just for this problem?
Yes. There's no partition function that has a 1/16 dependence.
So you'll give us the...
Yeah, like if you say in this equation, what is the, here's a new mass, or here's a new whatever, what changes with the partition function or something like that, in this equation. Yeah. Okay, so we end up with 10,000 divided by 298 times 5,000, right? No 1/16, and it's 167,000. So P2 is equal to 167,800. Okay. So the exponent matters, obviously, duh, right? But a lot of times people get sloppy and they're like, oh, temperature went up, temperature doubled, so this must have doubled. No, what's the power that, and there's a weird one. There's like 7 halves or something, or what is it in the translation one, 5/3 or something. It's so ridiculous. 5/2. It's really weird. Okay, so I think you're well prepared for Monday, and this video is on here, so I'll put it up.
So are those powers given? Like, are those equations?
Mm-hmm.
I'm just a little confused because I think I missed that on the homework.
Okay, so let's go back here, right here. Yeah, this is what I'm talking about. Temperature to the 3/2 power, and then temperature here to the 2/2 if you want to keep it in halves, right? So temperature for translation is to the 5/2 power. You see what I'm saying? Yeah. Or over here in rotation, temperature to the 3rd, temperature cubed. So if I double the temperature, it's going to go up by 8 because it's temperature cubed.
So would it be 3/2? Because then it's.
I'm just talking about just rotation. Oh yeah, 3/2. I'm sorry, I didn't see the 1/2. So 3/2, right? And then here, this one is not so easy to figure out. Okay, the proportionality, but you have the equation. You know. Yeah.
I have a question for the lab.
Okay.
I don't really know how to fill out this log from the